Assalamu alaikum warahmatullahi wabarakatuhu. Rabbi shrah li sadri wa yassir li amri wahlul uqdatam min lisani yafqahu qawli. Rabbi yassir wa la tu'assir wa tammim bil khair. So in this today's video we'll continue our topic of the single phase induction motor. So in the previous video, we have seen that the single phase induction motor is not self-starting. So we have to make some means to rotate it or make it a self-starting. For single phase induction motor to be a self-starting, so we have these three major techniques. One of them is the split phase windings, capacitor type windings, and shaded stator poles. So all these three techniques are methods of making one of the two revolving magnetic fields in the motor stronger than the other, and so giving the motor an initial push in one direction or the other. So in this way, by using any one of these method, we will be able to make this induction motor self-starting. So let's look at the first method, which is the split phase induction motor. So what happens in the split phase induction motor? We have these two. We will actually have two the windings here. So one of them is the main winding, and the other is known as the auxiliary winding. And here we have the centrifugal switch. So these two, we have these now two stator magnetic stator fields. One we called as the main field, and the other one is called the auxiliary winding. So two windings are set 90-degree electrical degrees along the stator of the motor. Remember that the main winding is low resistance and high reactance, while the auxiliary winding is high resistance and low reactance. And the auxiliary winding is designed to be switched out of the circuit at some set speed by a centrifugal switch. This is our centrifugal switch. Normally around 75% of the speed of the motor, this centrifugal switch automatically cuts off this auxiliary winding. So the current in the auxiliary winding leads the current in the main winding. Here we can see because it has a high resistance and low reactance, so the current will be leading as compared to the current in the main winding. So that will help this motor to produce a unidirectional torque, so that it will be rotating in one direction. So as we know that Ia lags by V because low reactance and high resistance, and Im lags V by very large angle due to high reactance. So starting torque is proportional to sine delta, and normally we switch off this auxiliary winding around 75% of the rated speed. Obviously, still this split phase induction motor has a very low starting torque. Now, this is the relationship of the main field and auxiliary windings. Here we can see in this graph that this is Ia and this is Im. Both are obviously leading, but lagging, and which we have this line voltage. And Ia is leading as compared to the Im. So since the current in auxiliary winding leads the current in the main winding, the magnetic field Ba peaks before the main magnetic field Bm. Since the magnetic field of auxiliary winding peaks first and then the magnetic field of the main winding, there is a net counterclockwise rotation in the magnetic field. In other words, the auxiliary winding makes one of the oppositely rotating stator magnetic fields larger than the other one and provides a net starting torque of the motor. So remember that in the double revolving field theory we have seen when we just supply the single phase to the induction motor, and we have no means, any other means, we just have the main winding, so it will produce two magnetic fields. So this auxiliary winding will actually strengthen the one of the fields that is produced by which we have seen through the double revolving field theory. So that will actually make it stronger, and that will help the rotor to rotate in any of the direction. That totally depends in which way direction we have set the field auxiliary winding. So here we can see that the torque speed characteristics of the split phase induction motor. So this is the main field winding alone, which we have seen that there is no starting torque. But with the auxiliary winding, we have a certain amount of starting torque that can be used to rotate it. So around 75% of the rated speed here we can see that we have switched off this auxiliary winding through centrifugal switch, and now the curve follows the main winding alone curve only. So here, because we know that once it's been rotated, it will continue to rotate in the direction which direction it is rotating already. So in a split phase induction motor, the current in the auxiliary winding always peak before the current in the main winding, and therefore the magnetic field from the auxiliary winding always peaks before the magnetic field from the main winding. So the direction of rotation of motor is determined by whether the space angle of the magnetic field from the auxiliary winding is 90° ahead or 90° behind the angle of the main winding. So angle can be changed from 90° ahead to 90° behind just by switching the connections on the auxiliary winding. So we can make them rotate in any direction. So by just keeping the view of this auxiliary winding uh, connections. So the direction of rotation of motor can be reversed by switching the connections of auxiliary winding while leaving the main windings connections unchanged. The second method is to use the capacitor induction motor. So the capacitor induction motor is again the same thing that it will strengthen one of the magnetic field in that we have seen in the double field revolving theory. So for some applications, the starting torque supplied by a split phase motor is insufficient to start the load on the motor shaft. So in those cases, capacitor start motors may be used. So in a capacitor start motor, a capacitor is placed in series with the auxiliary winding of the motor. So capacitor start motors are more expensive than split phase motors, and they are used in applications where a high starting torque is absolutely required. So typical applications for such motors are compressors, pumps, air conditioners, and other pieces of equipment that must start under a load. So there are three methods we can use to place this capacitor in this single phase induction motor. One is the capacitor start motor, one is permanent capacitor motor, one is the capacitor start capacitor run motor. So let's look at this capacitor start motor. In this we have just placed this capacitor in series with this auxiliary winding, and we can see that now the current is leading of the current of auxiliary winding is now leading approximately 90°, and IM lags the V due to high reactance of the main winding. So due to capacitor IS lead V, high starting torque. Applications are lathe machines, drilling machines, fans, etc. So here we can see that our speed characteristics. This is just with the main field only, main winding only, but and now due to the capacitor we have this starting torque is almost more than 300% of the rated torque. So here we have this, we can switch off this using the centrifugal switch, and we will again follow this the normal curve of the single phase induction motor. So the other one is the permanent split capacitor or capacitor start and run induction motor. So permanent split capacitor motors are simpler than capacitor start motors. The starting switch is not needed now. The normal loads, they are more efficient and have a higher power factor and a smoother torque than ordinary single phase induction motors. However, permanent split capacitor motors have a low starting torque than capacitor start motors. The capacitor must be sized to balance the currents in the main and auxiliary windings at normal load conditions. So that's why we cannot have the capacitors, any capacitor that can be placed. So here we can see here that we have just removed the centrifugal switch, and we have made the capacitor such that these currents are balanced, actually IA and IM. Now here this is the here we can see that the starting torque is not much as compared to the where we have this centrifugal switch and we have the large capacitor. And now with the starting torque is not much higher, but it has some starting torque, so motor will start in the beginning. Now capacitor start, capacitor run are two value capacitor. If both the largest possible starting torque and the best running conditions are needed, the two capacitors can be used with the auxiliary winding. So motors with two capacitors are called capacitor start, capacitor run, or two value capacitor motors. So the larger capacitor is present in the circuit only during starting, where it ensures that the currents in the main and auxiliary windings are roughly balanced, yielding very high starting torques. And when the motor gets up to speed, the centrifugal switch opens and the permanent capacitor is left by itself in the auxiliary winding circuit. So here it is. Here we have these two capacitors which are parallel with the centrifugal with the auxiliary winding, and we have this centrifugal switch. So now we have the capability of high starting torque and the smooth running and the good power factor of the motor at the rated torque. The third method that we can use to make the induction motor self-starting is the shaded pole induction motor. A shaded pole induction motor is an induction motor with only a main winding. So instead of having an auxiliary winding, it has salient poles. One portion of each pole is surrounded by a short-circuited coil called the shading coil. A time-varying flux is induced in the poles by the main winding, and when the pole flux varies, it induces a voltage and a current in the shading coil, which opposes the original change in flux. So this opposition retards the flux changes under the shaded portions of the coils and therefore produces a slight imbalance between the two oppositely rotating stator magnetic fields. So the net rotation is in the direction from the unshaded to the shaded portion of the pole face. So here we have these two shaded poles. So from shaded to unshaded pole, it will start rotating here like this one. And this is the stator winding. So it has some starting torque in the beginning that will give us the initial kick in the motor. So these are some parts of the shaded pole induction motor. So here you can see these shaded poles. This is another picture of the squirrel cage rotor, iron core, shaded coils, and these are shaded poles. This is the main winding. So I hope you have understood that how we can make the induction single phase induction motor self-starting. So obviously that's why we normally use them as a special purpose motors. Sometimes because we have to make some necessary arrangements to make this single phase induction motor running. So you might have seen the fans in our homes. They use the capacitor start capacitor run motor. Capacitor run motors, and they have only one capacitor, and that's continuously inside the motor, inside your motors, and that actually gives you the smooth and good power factor in the motor. So fans you might have seen your washing machines, the motors used with the water pumps, and all those single phase motors you might have seen. They you may see a capacitor that's with them, that's used to give them this starting torque. So I hope you have understood how we can make this induction motor, single phase induction motor, make self starting. Still, if you have any question, please feel free to ask. Assalamu alaikum wa rahmatullahi wa barakatuhu.